There she is. She's already host.
Oh, well, that works.
Okay. So you're doing the first one, right, Lucian?
Yep, I got the morning.
All right.
I assume we're giving people a few more minutes to show up.
Up to you. You're the boss in this morning.
I'm the boss. I'm so in charge. We have, what, 31 people right now. Veronica, do you remember how many people we had in general? Like for yesterday?
About 50 to 55.
Like actually logged on at one time? Or?
Yeah. Towards
Okay.
the beginning of the session. I think towards the end, just because of time zones, people miss out the later session. But for morning,
Yeah, that makes
it was
sense.
around 50.
Okay. Doesn't look like I can pause the recording. If we want it, we probably don't need, we were waiting for people for 5 minutes, but. All right, well, good morning or afternoon or evening or middle of the night, depending on your local time zone. My name is Lucian Smith. I will be talking today about model repositories and source control. And I'm actually gonna, here, I will share my screen. Yeah. So I'm gonna focus in two sections. The first one, I'm gonna talk about source control, and we have an exercise about that. And then after we've done that, I'll talk about model repositories in general, and then have a particular thing where I'll do a demo going through a biomodels model. So source control. So source control is basically what you did, when you did it, and why. So source is just, it was named after source code because it was developed for computer people. But it really can involve, it doesn't have to involve like source code for a program. It's anything, any computer document that you are creating. So it could be your model, it could be the paper that you're writing together. Like if you've ever tried to write a paper with 5 co-authors who all want to contribute a lot, it can be really an issue trying to like email the Word document back and forth, and then 2 people edit the Word document at once. So you're like, how do we merge these back together? That sort of thing. So control is then tracking and storing how your source modified with time. So I'm sure there's going to be a fair number of people here who are familiar with source control, but there's also going to be a bunch of people here who aren't. I'm hoping to like catch everyone up, and also make an argument, especially in the exercise, about why source control is useful even for model creation and stuff. So if you have a source code repository, it's sort of like an iceberg. You have your current version that you can see, and if you go to it, you just see that current version. But underwater is all the other versions that you have created up until that point. So if you ever need to know anything about the previous versions, you can go back and check. There are a variety of options, general programs that let you do source control. The classic is SVN, or Subversion. It's was used for many years. I used it for many years. It's solid. It was sort of a step up from CSV, in that it sort of cleaned a lot of things up from the one that was popular beforehand. The one issue it has is it can have problems merging things. Like if two people modify the same document, it can get fairly confused about if you try to merge things back together, and so you often have to do that by hand. Git is the modern replacement for Subversion, basically. Like in the last few years, it came along. It had a very different approach towards internally toward what it was doing. It's much better with merging. There's a lot of support for it right now. It is entirely over-designed, in my opinion. It has all these options, and because it was a new approach to doing things. So they're like, maybe people would want to do this, maybe people would want to do this, and they made a lot of things possible, and they made a lot of things that turned out to be basically the wrong defaults, the default. And so now there's a lot of things like, oh, when you do this, you should use this flag because you don't want to do the default because that doesn't usually do what you want. It will do everything, but it will let you shoot yourself in the foot in multiple different ways. I can't tell you how many times I've like gotten my Git repository into some weird state that I can't figure out, and the only solution is to literally delete the entire repository, recheck it out from scratch, and then go on from there. Another option is Mercurial. Mercurial was developed sort of at the same time as Git and sort of had the same philosophy with a different underlying code base, basically. It was similar to Git. It lost the popularity race in the years when it first came out. It's pretty similar in approach. Probably it's similar in being over-designed. I haven't used Mercurial as much, but certainly you're going to get a lot more support out there for Git. There's also an entirely different approach that is basically sort of continuous tracking. So like Google Docs just tracks everything you ever do, and everything anyone does, and it tries to be instantaneous. So there is no two people editing the same document in the same way, and there's problems merging, because every time you type a character, that character is then sent to everyone else, and they know exactly what you did. You can't edit the same thing at the same time, except in like rare race conditions sorts of situations. So it does complete tracking, but there's no comments. Like you can't say like, all right, I added this paragraph. I mean, there's no comments on the changes. You can obviously comment on a Google Doc, but there's no automatic way to say like, I added these 2 paragraphs about this. So it actually, here, I'm going to go to the collab and show you an option in there. So if you notice on the file menu, you can save and pin revision here, and then look at the revision history here. So this is like, again, this is sort of a Google Drive thing where everyone is sort of syncing at the same time, but it's not a character by character base. And you can, if you like, you can sort of pin the revision, say like, I'm saving this now to sort of preserve this for a bit, and have a comment about what I was thinking at the time, And then you can look at your revision history of the document as well and see all the times you've done that. That's sort of a built-in source control thing for Google Colab. So for the exercise and these examples, I'm going to use github.com just because it's by far the most popular today. I am hoping in the near future that there will be something that comes along that replaces Git, that uses all the things that Git got right and fixes all the things that got wrong, but I've been waiting for that for a while, so who knows. So I'm just going to walk you through the GitHub a couple of GitHub repositories I'm involved with. One, the sysbio GitHub repository is the Sarolab GitHub repository. So this is the sort of repository you might see for a lab that is doing computational things. The other repository I'm going to show you is just my own, and that is going to look like a personal repository. It's going to be like my own personal projects, some things that I have been working on. Source control is often useful. In fact, I think it's like critical when you have multiple authors, but it's useful even if you only have one. So let's go here. So here we have our GitHub account, sysbio, and you see we have 68. I'm going to zoom in a little bit because it's too small otherwise. You see we have 68 repositories, which is a bunch. Many of them are sort of old things that we haven't worked on in a while. Some are like this course has a Google repository and stuff. So some are sort of temporary things that are useful for a few months. Others have been useful for years. Roadrunner here at the top is the underlying source that runs all the simulations that we've been doing. It was last updated 5 minutes ago, so obviously it's been worked on it all the time. And here is GitHub's guess as to what the source code is written in, and that is correct. It is written in C++. This is so on GitHub you can have private repositories. This is something we've been working on to help clean up the actual biomodels repository itself. We've been working with that team on things, but we didn't want to have all those new models out there and having people accidentally find our repository instead of the official biomodels repository, so we marked it private. This is you guys, written in Jupyter notebooks, because that's mostly what it finds there. You can see its history here. The past year of activity. Didn't have a lot of activity until just recently. The other things you can see here is that it'll flag the license. So the MIT license is it tells you how you can use that source code yourself. Like CC0 is Creative Commons, MIT is it's an old. It was probably developed like, I don't know, probably I want to say the 90s, if not the 2000s. And it's pretty permissive. Like there's not a lot of restrictions on something with the MIT license. There's Tellurium. Tellurium is obviously written in Python. It has a big history, various other things here. Some of these, let's see here. So some of these we developed ourselves. The other things you can see though is sometimes it'll say like this is forked from this person's SemGen. So that's one of the features of GitHub in particular, and source control also, is that you can take someone else's source code, bring it into to the original repository and add yourself as a contributor to that team. But sometimes you want to sort of change ownership. Sometimes you actually do want to fork things and say like, we want to take it in this direction. I know you guys want to take it in the other direction. We'll just split. And in fact, if we go down a little bit, some of these things, I think, yeah, like LLVM 6.x, LLVM is another, it is the part of Roadrunner that actually compiles the model to machine source code. And that's a standard library package. And we used a particular version of LLVM, and LLVM has gone on, and like the way you use it, the API, it's called this, changed over that time. So we said, all right, we know we're using this. We're going to fork it here and sort of keep a copy. And we've actually made, like, as we find things that the main trunk has fixed that are affecting us, we've then like put in those changes directly. I'm going to click on that so you can see that. So here you can see that's a lot of commits. 279,000 commits is a lot. And if we click on that, we can see what the history is. And rolling down, this is us, this is us, this is us. So as of here, this is when we forked it. So in 2018 was the last time, that was their last version of LLVM 6.x. So I then forked it. I removed everything we don't need. I started making comments, and then we've made a few changes, a few bug fixes on our own since then. So when you're looking at something's source history, this is what you see on GitHub. And again, the other systems are going to have similar interfaces. It's going to show you the same information, even if it doesn't have a list exactly like this. But in general, this title here is whatever the person who made that commit checked in. And if you click on it, you can see if they typed anything else. This one, they didn't. Here, we'll click on this because that's a little bit. So in this one, the line was just a little bit long. So just cut out the first however many characters as the title and then continued it there. All right, I'll go somewhere else. I mean, here I usually have, yeah, here we go. So here's a commit that I made. I gave it a title just in general. This is a fix, so it compiled on macOS 10.9. And then I like typed out specifically what I did. This is very inside here. This is specifically how trying to get Clang to figure out something that was if-def out that you needed to take out in order for it to compile on that system. Let's see here. If you want to look at what specifically was changed, you can click here over here on this number. This is randomly assigned string of letters. Oh, that also, it shows you basically, so that was the comment. And then this is what I changed. So it was just one changed file, 7 additions, 7 deletions. Anything marked with a minus was taken out. Anything marked with a plus was put in, and it usually tries to highlight the differences. And in this case, you can see those are just a bunch of comments. And that's literally the entire change was here. I just took those 7 lines and I commented them out. So it says like 7 additions and 7 deletions and seven lines where I added a comment. And now it compiles on macOS 9. You can also, from here, this lets you browse the whole repository at this point in the history. So let me show you what browsing the repository in general is. So if you just look on the code, these are the directories and files that are in this repository. And this is a little README that's in GitHub. GitHub will display any README file that you have in there that shows you what it is. I've deleted a lot of stuff out of what was originally here, but here's the LLVM, and there's all the subdirectories. I don't know. Where's the main source? Utils or something is probably one of them. So there's like a bunch of stuff. I have no idea what Kill the Doctor is. That's hilarious. So obviously I'm not super familiar with this since this is someone else's code that we're just sort of fixing every so often. All right, we're going back. let's look at, let's see, are there any other types of things? So someone else's stuff that we're sort of using. Poco is another thing. We sort of forked it so that we could sort of pin it to a particular version and just use that. For HTML, Veronica is going to talk about SV Viper. You heard about SV Stoat. You might hear about SV Viper this afternoon. I'm not sure. There's another Joe's project. Our plugins, Antimony. Here, so Antimony was the very first thing I worked on when I joined Herbert's lab. Basically, Herbert hired me to say, like, please work on Antimony and do the thing. He had a previous project where he would called, what was
Jarnac.
Jarnac.
Yeah.
Jarnac was sort of the precursor to Antimony. It was both a model definition environment and a simulation environment. So you would type everything and then execute it all sort of in one group, which is basically what Tellurium is sort of turned into now, except that now all the pieces of it are split out. So the model definition language is now sort of split out to Antimony. He told me generally what Jarnac did, and then was like, but I want you to sort of look at it with fresh eyes, like develop things from scratch, and we'll see what happens. So that's the origin. It's had about 2,000 commits over the last many years. So like the last time the license was updated was 8 years ago. Oh, here we go. Comments you make 11 years ago. We've been working on this for quite some time, as I have either worked or not worked in Herbert's lab. There's the README. Yeah. So let's look at Roadrunner. So one of the other things about source control, and GitHub in particular, is that when you can set things up so that when you check something into GitHub, it will run things for you if you want it to. And in particular, you want it to run tests, because as you change things, you don't want to break things that used to work. As you're changing things, you want to add new features, but you also don't want to like kill old features. This is something I finally learned after like 8 years of doing Antimony. I was like, maybe I should check to make sure I'm not breaking things, because I was breaking old things all the time. So here's like, this thing right here, this little check mark, shows you whether it is passing the tests that you have told it to run. And if you click on just the little check mark, it'll show you more details. It says all checks have passed, 21 successful checks. Let's look at the details. So here's a list of all the things that we tell it to do. You can see how it's Linux build different things, Mac build different things, Windows build different things, many Linux build a few different things. So we're telling it to build stuff on a variety of operating systems. Anytime I change anything, it will go through and change and run everything and make sure that everything is there. We're using a system called Azure Pipelines, because that was what a person in our lab liked, Kieran. Before we were using that, we were using Travis. Different systems have different features. It really depends on sort of what specifically, it mostly depends on what you're comfortable writing in, as to what system you pick. So if you're comfortable with the system, just use that if you can get it to do what you want. And if you can't get it to do what you want, then you're gonna have to learn a new system, but hopefully you don't have to do that much. So we'll click on one of these things. So this is more specific to what Azure does, but Travis had a vaguely similar system. So we're looking, so this is the Mac build Roadrunner. I'm going to zoom in again. The 64-bit Mac release. And these are all the different things that we told it to do in order, and it tells you whether it did each thing successfully. Checks things out, it prints some variables, blah, blah, blah. This is going to be the build command. So this is when it actually converts all of our source code into an actual executable. We use CMake, which I would highly recommend in general for make systems. You don't need it for Python, for anything C, C++. other things. It's a good, we only have to write one CMake build system files for all different platforms. You don't have to say like, do you do this on Mac, do this on Windows, etc. There's some things you have to say in that file that are platform specific, but mostly it isn't. So scrolling down, you see it's building all these things. Let me a little bit smaller so I can see this. All right. You see it'll have warnings here, and I can, so if I want to go like sort of check the warnings, I can look at this and say like, oh, what, like it clearly worked anyway, but if it's warning me about something, it might be worth fixing. What else? And then, yeah, as it just goes through, it's telling you how far it's gotten as it goes. And this is actually, it's like all this would be when you actually compile things on your own machine, this is sort of what you would see as well. So usually it's not like I just rely on GitHub to fix everything for me. I will, I'll compile things on my own machine, but I'm on Windows and I won't check it on Mac and Linux. I will let GitHub do the Mac and Linux things. So then it installs everything, and then at the end it says like it's finished and it did successfully, did everything successfully. So that was, so first it just tests whether it builds. And then C-test is our test system that we have. And again, it just runs all our tests. So here's a test, C API exceptions. Is it properly throwing exceptions? Here's other tests. So here, so the majority of these tests are the SBML test suite, test 252. There are like 1,200 tests in the SBML test suite. The SBML test suite is a publicly available repository of models and simulation rules for how to simulate that particular model, and then the expected results for that. So, and it uses all the different features in SBML, or at least it tries to, and all the different features in different combinations, and all the tricky edge cases in SBML. It will say like, if you are interpreting this SBML correctly, you'll get this result. So if you are using any SBML simulator, you want it to be something that passes the test suite, because you want it to interpret your models the same way as everybody else should. So yeah, so like the vast majority of these tests then are figuring out all the, are running each SBML test suite in succession. Actually, so let's see here. Yeah, it doesn't have the details here. But so when it runs test 253, the test suite actually has, there's different levels and versions of SBML. So like over the years, it's been updated. So all these tests test whatever it is that they're testing in every single version. So what I've been doing is I'll take the earliest version and the latest version, and we'll test those both in Roadrunner on the hopes that if it does the first and last, that it'll cover everything in the middle as well. It'd take even longer if I tried to run literally every single thing. Most people, when they say they pass the test suite, they just do the latest that their software interprets. So that was testing. Let's go back. Why is this so? All right. What was it? Okay. All right. So that was that. So yes, let's go now and look at mine. So that's what a computational labs GitHub account is going to look like. It's going to have a bunch of stuff. The history is going to go back for years, all sorts of stuff. If you have your own personal account, it's going to look a little different. This is what mine happens to look like. So here's one, SBML to MATLAB, which says it was forked from someone else's thing. That was, so SBML to MATLAB was something that was written for the lab. at one point, it was my job to sort of update it. It hadn't been touched for a while. I wanted to make sure it compiled on modern systems again. Instead of, I was a little worried about like messing up the original. And in fact, if I forked it from Stanley Gu, that was his personal thing. I didn't want to try to edit things in his. So I pulled it over to mine, edited it there. And then I think I eventually pushed it back to the SysBio account. So now SysBio owns the current version of SBML to MATLAB. The sharing disease models, Jacob Barhock, that was someone on the SBML discuss list who was talking about like using SBML to model disease models and wanted to discuss things. So I pulled it over and worked on a few things. And this was basically like created entirely as part of a discussion online. Like it wasn't a project that I was working on. It was just like I was talking about something with someone and wanted some concrete examples and used GitHub to sort of further that. The stochastic distributed test suite was, so I actually have been part of the SBML team, and we are developing the test suite. I've actually like most of like all the modern tests in there, everything like from model 1000 on are tests that I've actually added myself. And for a while, we also had a stochastic distributed, so that you have ODEs, but then you also can model things stochastically. I don't think we've talked about that yet, but we may at some point. So I was developing some new tests for a new system that we had. I didn't want to make that part of the official repository yet, so I just sort of created them from scratch here. The other thing was I created it from scratch because I wasn't sure if it was the best approach. So I made it, showed it to other people. We went back and forth a little bit and we decided it was. And then after that, I ported it to the actual SBML, the official SBML test suite in the stochastic branch. Python was like Python programs I used personally when I was working in genome sciences in the CUNR lab. Cragny Manor. Cragny Manor, as you can see here, was written in Inform 7, which is the very popular programming language. Actually, no, I'm actually really impressed that GitHub knew about Inform 7 at all. Inform 7 is a natural language programming language that it is written for creating interactive fiction games. So interactive fiction games is when you see text and it tells you what goes on and you type in what you do and it tells you what the response is. So this was obviously my personal, like, you were talking about personal project, this is definitely a personal project. It doesn't have a lot of commits, it just has 19 things. But Cragny Manor was actually a project. It was like the anniversary of some really popular game from years ago. Someone decided that they were going to get a bunch of people together and assign each person a room in a new game without telling anyone what any of the other rooms were. So I was assigned this room. It's in town. There's a drinking fountain. That would go like make a sort of a vaguely horror-ish game like the original game. So if you look at my commit history, this is the entirety of it. I made some things, put in some sketchy comment, eventually like developed the room. And then I had people beta test it. And so then at the later things, you can see bug fixes. I like this one. Now everything should be working. And then small changes, more bug fixes, because of course that happens all the time. If you want to edit things, so I've just showed you like what it looks like on GitHub. And for the purposes of this class, I'm just going to ask you to do things just online because that doesn't require you to do anything to your machine. But source control is almost always going to be most helpful if you have something installed on your own machine in the end. So you are actually working in your native environment, whatever you like, you can make some changes, and then you push the changes you made to GitHub officially. And then you keep working, and then you push more changes. And if like your tests fail, it'll email you back and say like, hey, your test failed. And you're like, oh crap, what did I do? But in general, that's what you have to do. So, but you can just edit things online. So like, here's my README. It doesn't say much. I don't talk about like what the actual project is. So how about how if we edit it? So this is the edit button for the README. If you click this, it'll take you to this. And I just want to know, I'm just going to want to put in the link. So I'm going to put a new thing there. Fragmenting Manor. Here it is. This is the actual page for the actual game. You can actually play it here, whatever. Copy that, close that. Full game at whatever. Done. So this is the editing window here, and at the bottom I can say I commit the changes, and it gives me a default title. If you remember, everything had a title like what you were doing. So I'm going to call this add link to full game. And if I wanted to say more, demonstration for a workshop. If I have a couple accounts, so it would let me do either email address, or I guess email addresses here. And then it says I can either commit directly to the master branch or create a new branch. I'm not really going to talk about branches much here, but basically, branches are often useful for when you have something that you want, especially if it's for a public-facing source control system. You want something that will always work for everyone else, and then you want the things you are working on right now that might be broken. So you will probably usually at least have two branches. You'll have the public face, and then you'll have what I'm working on. And if you have multiple people in the lab, sometimes you'll have the public face, and you'll have what I'm working on and what someone else is working on and what other things. In fact, I might show you that in Roadrunner because that'll be more illustrative there. But for this is just my personal project. I'm not going to branch anything. I'm just going to do that. So I'll click commit changes, and bam, there it is. That's the new README. And if I go to the main thing, now it says remember full game here. And if we look at the commit history, we can see here's my new commit 3 years after the original. So I said I was going to go back to here so you can see the branches. All right. So here it says how many branches there are. There are 20 different branches. And if you want to switch to one, you can use this. This is the develop branch. So by default, we have the sort of the things we're working on, and then we push things to the main directory, other places. So some of these branches are like issue 711, issue 762, errors leaked by Simulate, whatever. So it's sometimes there are bug fixes, like, and this is a particular bug. In fact, let's go. I will show you issue 711 in a bit. Different things that people have been working on. Pickle plugins develop. Plugins develop merge. Plugins develop merge exists because of Git's over design. Because I had a branch and I had a bunch of changes I wanted in it, and I sort of took a long time, and there's a bunch of changes in there that I don't know, it was sort of wide ranging and it spanned a long time. And then there was the main develop branch, which was also moving on for quite some time. Eventually I was like, all right, my branch is good. I want to merge it back in. And when I merged it back in, it just didn't do it right. There were all sorts of changes that I had made that were just gone. And I fought with Git a little bit and I couldn't get it to work. And finally I'm like, I'm doing this by hand. So I just made a new branch and I literally copied my code from the old branch into the new one. And that's the result of that one. So that's what happens when you have to fight Git. All right, last thing I'll show you about GitHub in particular is that GitHub lets you file bug reports or issues, as it calls it. So this is if anyone in the world wants to say like, hey, I'm running into a problem with Roadrunner, they can come here and say like, and file say like, this doesn't work in Roadrunner and this is what I needed to do. And sometimes it'll be because sometimes the answer is, oh, you should be doing this other thing. We should update the documentation. Anytime someone is finding a problem with your code, there is a problem with your code. It's either a problem with documentation or it's a problem with the source code. So one of the tricks of responding to issues is that you have to figure out which is which. So like this is a request. Matthias, who's in Germany, who often works with us, and he would like this particular function to be available in the Python interface. Great. I told you I was going to show you issue 711. Let's go to 711. So this was another one. So this, he's saying like, as your, here's his Python, right? So if you do this, he's like, this is my Python code. I don't see why this wouldn't work. And I get an error, like invalid ID for initial model. It's like, all right. So how is it supposed to work? And so we then, did we discuss this? No, it looks like, so I just, I didn't assign myself, but obviously we have a branch of Roadrunner that's designed specifically to address this particular problem. So in that branch, we're working on things. We'll try to fix it and submit things back. Oh, you know what? I bet this is chat things. Let me look at the chat real quick. Da-da-dun. All right. Oh, so yeah, so yes, you're right. Someone else saw 66 repositories. Some are private, so that's why there was slightly different. I showed you the one that was private. A commit, yes, a commit is a unique change that is made to the file. So if I'm editing something, I make a change and I commit it. That means that it is now tracking what was changed and when and what my comments were at the time. Git ignore is a file. That's just the file that tells you what, tells Git not to track changes to specific files. Stochastic and probabilistic, yes. So stochastic is random. So sure, let me tell you a little bit about stochastic modeling. In stochastic modeling, you have few enough things in that you're modeling that it is not appropriate to treat them as bulk and treat them as infinitely divisible. So like you notice, like as you run through our simulations, the concentration of something might be 5.74, and then like that it goes really long. Like the concentration is a really long number. That means, and that's a very precise number, and it's wrong because the concentration of ATP is not actually that long. There's a particular number of ATP molecules in your solution, and you can't change like there's a number that's either you have one or you don't. There's like at the fundamental level there's a count. So normally it doesn't really matter. You can make that assumption that there's enough that you can treat it as a continuous curve. But if you only have 100 molecules of ATP in your solution, you're going to want to actually model that as 100 molecules. And 100 molecules have the properties they don't behave exactly correctly and exactly in step with everything else. They wander around the solution randomly, and until they bump into another molecule that's supposed to interact with, it doesn't happen. And then on average, that happens at the rate at which you say it happens. But specifically, it will sometimes happen a little bit early, sometimes happen a little bit late. So when you are modeling that, you want to say that's a stochastic modeling system for when you have small concentrations where you actually want to treat things as individual items. A little bit about the different licenses. Licenses are, so yeah, licenses mean how can other people use your code, and do they need to, can they use it at all? And the answer is usually that like they have to, if you want to make it, if you want to call it sort of open source. that's not, okay, that's not true. In academia, most things are public, other people can use it because it's been publicly funded. The NIH says, like, here's money to do a thing for the good of the community. You do a thing, it has to be good for the community, right? Sometimes you can just, the license is like, use it, do whatever you like, I don't care. There's usually some sort of clause in there. It's like, just don't blame me if something goes wrong. Other things are, yes, you can use it. Don't blame me if something goes wrong. You have to tell people that it was me who made it first. Yeah. Other licenses are sort of like they sometimes call them viral. It's like, you can use this, but then you have to also make it open source, and you can't then do anything closed source with it anymore. And that was really popular in the 90s. And then people started being like, actually, this is really restrictive because I want to use this in industry. And now the industry can't use these well used things. And so the movement has gone away from those. And now I don't even remember what the name of the silly license was. Anyway. There are pretty restrictive licenses in terms of like what you can do with it. And in general, I mean, like anything on your list is going to be fine. Like the CC is Creative Commons. That's if you, like, the CC0 is basically like, you can do it whatever you like, just leave my name on it. Or if you change it, take my name off of it. That sort of thing. Those are the sorts of things that go into those licenses. Stochastic. Oh, there's good thing for licensing. Random walk. How do you design tests for your code? That is a interesting question. Yeah, and Veronica says we'll talk about how to design tests for your code this afternoon. But yes, it's really important. Like as I mentioned, I was like the developer for the SBML test suite. So I was not only designing tests for us, but I was developing tests for everyone that uses SBML. And you just have to think, like, what can go wrong? What is the weird edge case? Some of my proudest moments of those in that capacity was when I figured out a weird situation that had actually been there for 10 years and no one had noticed. It's like, if you do this and you also do this, then like this weird thing happens and everyone's like, really? It's like, I guess that's true. So I put in the test and now you make everyone else have to like deal with this thing that you found, this weird edge case that like literally no one has ever noticed in 10 years. But generally it's a lot of thinking. It's a lot of thinking about things, and it's a lot of noticing things. Every time you find a problem, every time someone reports a problem, you want to put that in as a test case, so that it doesn't become a problem again. Veronica has a good answer about what forking things means. That looks good. All right. Wait, is there more chat? Did I miss one? Okay. And now I know if this thing pops up, it's because someone's chatting. All right, so let's see if we've covered everything I wanted to cover. It lets you track and fix bugs, lets you auto test your code in some cases. It is a record of everything you did. We're going to be doing more about that later, because that can actually, the fact that it is a record of everything you did can be very helpful in tracking and fixing bugs. That's going to be the exercise in a bit. And it lets you sync with other people who are working on the same material. The fact that it's publicly available means that others can then examine your code also. So if Roadrunner is publicly available, all our code is literally online. You can look at any line that you want. So if you really need to know for sure that your simulation is doing the right thing, in a weird case, if you needed to, you could go and look if we are unresponsive, or if we've like abandoned the code 10 years ago because we've lost funding. You can say like, all right, I'm going to look at the code and see what it does. Like what's literally going on. if you decided that like, okay, this was 10 years ago, they lost funding, it's still there, I want to sort of revive it, I can grab it and I can be the new developer of it. You can fork the code to do your own thing. Or like we said for our, like for LLVM has moved on. We're using this particular version. And so we're forking it just for our own purposes. And then others can also submit bug reports. So yeah, I think I've talked about all those in context. So one of the things that we asked you to do was to get a GitHub account. If you haven't done that, then you should. This is just for reference. If you're looking at my slides, you can like look on creating a new repository. I'm going to walk you through creating a new repository. And then as the first exercise, you will create your own repository. So let's do that. We'll go back to mine and we'll minimize this. So if you want to follow along or just watch and then do your own, either thing would be fine. So yes, it is actually possible to use GitHub for any non-text-based files. The only issue is that for like binary files, if you remember the little difference I showed, it like showed you the 7 lines that have been deleted and the 7 lines that have been added and exactly what changed. That it won't be able to do that for binary files, and I don't know if it can do it for Microsoft Word, because Word underneath the hood is sort of, I guess it's a zip file of text, but so it can tell you, yes, this was the old version, this is a new version, but if 2 people both change it, it's not going to be able to merge them itself. It's going to be like it could if it was just text. If it was just text and I added a paragraph here and you added a paragraph here, then it could say like, all right, then we'll just add the 2 paragraphs. But a Word document, since it's all just sort of a black box, it says like, these black boxes are different, good luck. But you can at least say like, oh, someone else changed it, that sort of thing. So let's go, we're at repositories. So you go to your account, you go to repositories, and you click new. There are some other templates that I apparently have for other things. I'm not going to worry about that. I'm not going to create any template. So new repo demo, there we go. And then we'll give it a description. Demonstration. We'll make it public. And then we'll go ahead and add a README. You could learn more about git ignores. This is just a demo. I'm not going to add that. And I will go ahead and choose a license. I tend to do BSD just because that's the one I'm familiar with. And basically it's do literally whatever you want with it. And then I can create the repository and it will set the main as the initial branch. And here we are. That's basically it, right? I can edit the README then. And I'm going to give it a nicer name, new story. And then the little comment that I made is automatically added as the demonstration here. I will not accept the defaults and just commit the changes. New repository, ta-da. That's the entirety of what it takes to make a new repository. Now, the next thing I'm going to ask you to do is create a new file. Let's see if I can do that. Oh, that's right. Okay, so I was looking. So here, let me show you what I did. So here you see the URL, it's new repo for demo blob main readme.md. So I'm looking at the actual, right now I'm just looking at the readme file. So if I go back to the core thing from here, I can look at that, add file. So I'm going to add a new file. I could upload a file if I have one on my desktop that I wanted to. I'm going to go ahead and just create a new file here. I'm going to call it test.py. And then I can edit my new file. Oh, here it is. So what I'm going to do is I'm going to go back to here and I'm going to grab one of the other one of our Python notebooks. So here we have this. I'm going to copy this. So I went to my notebook. So copy something out, go to the new file and paste it in here. And I guess I'll just leave that. Sure. Great, test.py. That's great. Commit directly to new branch. Great. Commit. Bam. Now I have test.py here. So now I can go here. And if I want to say, actually, I want to like have it actually do a thing. So I will edit it. And then I will say print yo. And then load a species a equals 3, which is about the smallest model I know how to do. Oops. R equals that. Simulate r dot plot. Right. Commit those changes. All right. So I've committed the changes. Now I have a little program. And again, working online is not the way you eventually are going to figure out how to do this, but it works for demonstration purposes. So here, if I click raw, then I actually go to, I get this. And if I wanted to, I could download, I could like right click, save as, and it would save as test.py on my machine somewhere. For now, I'm just going to copy that and then go back to here and say paste code here, right? So I will paste my code here. I'm going to go, well, you know what? I'm going to go ahead and run it because this is the first I need to install Tellurium anyway. We'll run it. And then it's going to take a while because it has to install Tellurium. But that's what it does. So that's I basically just walked you through the entirety of the first exercise. So I will give you, I can answer questions, go do that, go through exercise 1. We'll meet at 10 minutes or so. I think should be fine. Just 10 after the hour. It's 9 o'clock right now. Start the. All right. Hopefully everyone was able to figure out how to do that. If you didn't, don't worry about it because I'm going to ignore it for the rest of the talk. Yay. The next thing, what was I here? So the next exercise is a little bit more involved. I call it what went wrong. So we're going to look at a repository I created for this purpose. Like I literally so here is a Python script. If we can click on it, here we go. This actually works if you in just straight Python, but if you paste it into the exercise, it'll work there. What I'm going to have you do is there is a problem in this model. Oh, right. Thank you. Okay. Right. So let me go back here. To one of these things here. Okay, exercise 2. What went wrong? I clicked, we're clicking here. This is an example I created just for this exercise. Nope, this isn't the right one either. This one is. Okay, here we have network modeling 2021 example. There are 26 commits. I've made them all over the last few days. If we look at the Python script here, analyze wolf glycolysis. This will work in raw Python, but you can also cut and paste it into Colab if you do the install Tellurium first, which I put in the example, the exercise template on this directory. So if you look at source control exercises, you can just use that file and then continue from the bottom. I don't need this one anymore. There is a problem in this model. This model is supposed to oscillate, and it does not. And this is one of the things that I find source control absolutely invaluable for. At some point, I'll be going along, and someone will notice that something's wrong in it. And I'm like, I know this used to work. At some point, I broke something. What on earth happened? And if you have the commit history, you can actually go back and check. So one of the things that I find myself doing, and that there's nothing else like it, is to sort of like, I'll go back halfway in time, I'll check it. Did it work then or not? Yes, no. And if it did, I'll like go back and forth until I find the actual point at which, when I made this commit, this is when I broke things. And then once you know that that's the commit where you broke things, then it's much easier to find what went wrong then. So let's look at the commit history. So there are 26 commits. I tried to be verbose in my comments. You will hopefully find out why being verbose in comments can be really helpful. And I want you to find where in this history I made a mistake. One of the most useful things you're going to find if you're doing things online is this button over here. So like here, I changed NA to NAD. If you click this, you can browse the repository at this point in the history. And then you can click on this and actually say, like, this is the actual thing. So if you go here, copy this and put it into a cell, run it, it'll run just this. Similar, and then if you wanted to know what was going on, you can click on the on this, and there's my comments, and then you can see like what the actual changes were. So this was a element that was called NA. I changed it to NAD, and you can see all the different things. And you can see, including here, it changed from display names to display NADMEs. And that is in fact the bug that I then fixed next. If we go back, typo fix, sigh, right? NADMEs back to names. So there is the mistake that I want you to find is the mistake I put in there on purpose. All the other mistakes were genuine mistakes that I actually made, that I went ahead and committed anyway, just so you could see people making mistakes, because mistakes actually happen. Yeah, go for it. Let's take another 15 minutes for this. This is a little bit more involved, but that should work. Basically, yeah. Run the most recent version. Didn't work. It doesn't oscillate. Check the very first version that has that file in it. Check that. Watch it oscillate, and then go through that history. I would recommend sort of jumping and sort of bracketing it, and trying to find what happened and why. Then, and I'll be able to know if you do this, I want you to file a bug report and describe what the issue is. So on here, if you go, someone has a question. Easy way to copy the Pi code instead of selecting scrolling. What I did, so if you click on it, if you click raw, and then you can just Control A is all, and it'll copy it. That's probably the simplest, I guess. If you manage to get on your own machine, you could actually check this out and then switch to particular revisions if you want. But if you're doing things online, I was able to do this relatively quickly by just doing that sort of thing. Now I forget what I was about to say, but anyway. Oh, right. Issue trackers. So once you figure out what the problem is, go to issues and file a new issue and tell me what the problem was. And then as an advanced thing, you could try to create a fork and actually fix it yourself. And for extra advanced, there you can actually like try to push your change back to my repository to say like, I've fixed your code for you. Here is the fix. So if you have lots of time and want to try this sort of thing, you can go for that. And at least, even if you don't, just know that that is a thing that people can do. Any other questions about what the assignment is? Stop sharing again. All right. Right, good luck. I'll see you in a few minutes. I'm going to mute myself again. We could probably pause the recording. Recording again, and we can chat again. All right. So, a bunch of you found the error. Good job. So here, I'm going to show you from here. So I have answer source control exercise here. And what I did in this is I did. Okay. Share my screen again, of course. Thanks. Okay. So from here, one of the files is the answer to the source control exercise. What I did is I took the original thing and I actually just pasted in the code, and you can sort of watch what happens. So at the beginning, I just load the model straight from biomodels. It oscillates. Then I do a few things, like I changed like the number of points I collected. I changed the time frame. And then I got the Antimony string. I told it to print it, and then I replaced, instead of load S, now I have load A, and I placed it in what I had before. And then you can start seeing what happened there. You can see, if you're interested in finding other problems, you can see those as they go. These are all oscillating. They're still oscillating. And then here, wait, look, it crashes and it stops oscillating. So what happened here? And if we were, here, let me look at the chat real quick. Okay, I'm glad you enjoyed the exercise. Good. I was hoping that would happen. Oh, here we go. So actually, here, let's go to the issues. So yes, here are everyone who's filed the bug report. Thank you all. And here's the link. Value of K0 dropped. So we're going to click. They actually thank you for providing a link to the fix. So here we see in that change, we changed K0 from 50 to 4.82 and K4 from 80 to 77.77. So then you may be like, why did you make those changes? And the only answer is going to be like, either you have to read my mind, or else you could look at the commit message. This is, again, I put this in here specifically so you could see the value of commit messages. Literature fixes from PubMed 000xxy. In other words, I made it up. The K4 should be 77.77 and the K0 should be 48.2. You may notice that I didn't actually make it 48.2, I make it 4.82, and that's the bug. So by looking at the different changes, you were able to find what the change was. By looking at the commit message, you can figure out what the right thing was. And I sort of obviously cheated by providing enough information here. But even if I just said literature fixes from PubMed 000xxy and didn't say what they actually were, then you could go look up that PubMed article and say, like, did they really think it was 4.82? Why did they do it? And then you look it up, it's like, it wasn't 4.82, it was 48.2. So, so if let's do a find and replace on this whole thing, the 4.82 and replace with 48.2. And this is and we'll do a replace all, and then we'll run all. So you'll see before, here's all my crashed plots, and now it's like it just deleted them all. So this would be what would actually happen if I hadn't made the mistake. As we were chatting with a little bit with Polly, you can actually just take the last version fix, if you fix it in the last version, then you should and see if it oscillates there, then that's all you really need to do. And it probably shouldn't have tried to run literally everything, but anyway, where are we at? Ah, here we go. So there's our changes. There's a little, this is a problem when I changed thing. I don't remember what I did. Anyway, I did something wrong, then I fixed it in the next one. Oh, it didn't, okay. So it did something, it found a problem and it wouldn't run it again. So here, we're just gonna run it anyway. Runtime, run selection, and run after. So you can see, oh, look, it's oscillating again. Oh, here, we're gonna skip that problem. Or here, if I go here, if I run after, is that gonna work? This was an interesting one. It's officially oscillating, but I made a mistake that sort of makes this concentration go negative, which I then fixed in the next one. But it's nicely oscillating. All my changes are doing stuff, and here at the end it still oscillates. So that's that. All right, does anyone have any questions? And if anyone manages to like figure out how to do the fork and recommit, great. I'll see what I'll show. Oh, hey, look, pull requests. Nice. So, okay, here. So a bunch of people filed bug reports. I'm getting emails about them, which is good. And possible wrong value.
Question.
Yeah.
You share your screen.
I stopped sharing. You're right. You're right. Okay. Yes. Okay. As I was saying, I'll go to the issues. So here are the things that you all have filed. Model stopped oscillating. Possible wrong value. Okay, 48.2 and not 4.82, etc. So we actually have a couple pull requests. I'll show you what those are. So someone forked it, they made a mistake, and then they say, and then they're asking me basically through the format of Git, here is a fix for your thing. Obviously these are probably going to do the same thing. Tells me there's no conflicts. And if I go to the files changed here, this is a change that changes 4.82 to 50. Now, remember in the comment, it should actually change to 48.2. So I might not do this one, but it's a good demonstration. Someone else had a comment. What's your, my comments are hiding. I can't see them. I don't know why. Anyway. I'm gonna go on. Let's look at this one. Your first contribution, yay. Files changed. There we go, 4.82 to 48.2. So I can review the changes. This is correct. Shoot, anyway. I accidentally clicked the button and now it's not letting me do the thing. Files changed. Oh, this is right, there we go. I can click approve. I can submit my review of the change. Then I can merge the pull request. Click here. Fix the oscillation. Actually, it makes me type something here. Oh no, it doesn't make me type anything. I can just hit confirm merge. Sometimes it'll make me type a thing. There, I have now confirmed the merge. If I go back to my code, go to analyze Wolf glycolysis, we go down and K0 is 48.2, as it should be. If we copy and paste this, it will oscillate. Good job, everyone. We solved the problem. Yeah, the pull requests are somewhat advanced. Oh, you figured it out, good. Yay. Yeah, so feel free to continue to mess around with that thing. It was designed exactly for this class. I'll probably delete it in a few weeks or something, but so good job. Yeah, all right, that ends part 1. Let's take a 5-minute break and we'll go on to part 2. All right. I'll share my screen again. Close that. Close that. And close that. And go on to part 2. All right. So for this part of the talk, we're going to talk about model repositories. And it sort of ties into a little bit of the last exercise, because the last exercise we were using a model from biomodels, and what I was doing was messing with it. And that's what we're going to do again, sort of in real time here. Model repositories are places that are repositories for models. They contain models, often SVML or CellML. We may not have mentioned CellML before. CellML is another model format, mathematical model format. It is different from SVML in that SVML is sort of reaction centered. So the fundamental unit of an SVML file tends to be the reaction, like A goes to B. In CellML, the fundamental unit of what you store is math. And usually for reaction kinetic, like ODE models, then the math is the dsdt, the rate changes. So if you want to know what the reaction network is, and if you are interested in the reaction network and how things are related to each other, you have to use, you're going to want to use SVML instead of CellML. CellML will just tell you, like, here are all the terms of how S changes in time. And if you want to sort of recreate the reaction network from that, you can, but you have to sort of do that by hand. CellML is often used in more macroscopic physiology, like there are CellML models of a beating heart and that sort of thing. But in general, the fundamental unit of CellML is math. The fundamental unit of SVML is a reaction. Model repositories can be either curated or non-curated or both. By curation, and what I mean is that there are people who actually go through and make sure that the model that's in there matches matches the truth. And usually that means matches something that's been published in the literature. Some like biomodels has a curated branch and a non-curated branch. Everyone can update things in the non-curated branch for their own purposes, and eventually if it gets curated, then it gets moved into the curated branch. And the different repositories have different purposes. So depending on what you are interested in, you might find a bunch of models for your interest. I found this as a good list of a bunch of model repositories for systems biology in particular. Now, the SVML models for KEGG is first on this list because the people that made this list made that repository. So it's like by using our conversion script, KEGG to SVML. So someone the other day was asking about getting models out of something. So if you were wondering about getting models out of KEGG, this is what you would do. They have pulled a bunch of models out, put a bunch of reactions out of KEGG, made models out of them, and put them all together for you. Anything that's SVML is equivalent to Antimony. Antimony is sort of a viewer. You can think of it as an SVML viewer. There is close to a one-to-one correspondence between everything in SVML and everything in Antimony. There's a couple edge cases, but by and large, you're going to be able to get everything out of one that you could get in the other. Biomodels database, been around for years. It's a good source of models in SVML. Everything in the curated branch corresponds to an actual published paper. The general mechanism in the past of creating new biomodels is that the curators go find a paper, like this is a good paper, they will make the model from the paper and then publish it. This is often very hard because when you publish a paper about a model, you almost always either get something wrong or leave something out or both, or you didn't, because I don't know, that's just a big problem. I'm not I'm not going to get into it right now, but the take-home message is that if you make models, make your actual models available so that people can look at them and actually know what you're doing. If they want to like do anything with further with your research, if they have their model, they'll be able to do something with your research. And otherwise, it takes months to go through and try to extract all the information from your paper, go back and ask you like, what's this term? You forgot it. Are you actually doing this here? Or is it like, as you describe it in this paragraph, and you'd be like, oh, right, we changed our minds halfway through. Actually provide the model. That's my message. CellML repository is a repository for CellML in particular. It is interesting in that it has baked into it a source control mechanism. Originally, it was Mercurial, and I think they've converted to Git. But they actually, like, as a repository, they have a working space for modelers, and you can go back and see the history, just like we did with my model, of what changed when and how. So that's a really useful tool for if you want to extend the work of anyone that's done anything for the repository. In general, this is solid. When CellML was first developed, they did not have any simulators. It was just a description. And they had some curators that did a lot of hard work going through the literature and encoding everything in CellML and making them available at this repository. Many years later, 5-8 years or so, I feel like, they finally, maybe it was just more like 3, they actually came up with a simulator, and then they could go like and actually run all these models that they had been creating. But creating models from the literature has always been a strength of CellML. This is a long list. I'm not going to talk about all of them, mostly because I don't know much about all of them. But when we've talked about some of these earlier, I know Veronica mentioned a few. But this is generally just a big list to let you know that there are a variety of models out there in a variety of formats. Oh, here's one that's sort of interesting. We mentioned graphics, like pictures of reaction networks and how they are not super standardized, and that SVGN, the Systems Biology Graphical Notation, is designed to sort of help with that and make things a standard way of looking. So these are some examples of sort of standard SVGN or graphical notations for these files. All right. Veronica told me about this one, neuroscience. It's a bunch of neuroscience models, genome scales models at the big database, because they're big. But today, I'm going to talk about biomodels specifically. That's the one I'm most familiar with, and we have other things. So let's see. So as a demonstration, I'm going to find an infectious disease biomodel. So let's go to this place. So this is what you see when you go to biomodels. And all of this can be done programmatically. And I have never done it programmatically, so I'm not going to tell you how to do it because I'd have to learn myself. So if you want to, so they have a button here. So for submitting new models or updating old things, which is great. And in general, here we have manually curated models and their non-curated models. And the auto-generated models, sort of the three big branches of biomodels. The auto-generated models tend to be like the genome scale things. They're huge. You're not going to be, usually wouldn't be able to actually simulate one of these models, partly because they're incomplete. They wouldn't have reaction rates or parameter values. They just sort of tell you what the network looks like. There's different modeling approaches here. ODEs is what sort of the bulk of things. They have some constraint-based modeling, a few logical models, and like 5 PetriNet models. Let's look at the model of the month. Access this model of the month. So here is a biomodels model, and this is a little information about it. They've given you a graphics description of what everything is here. This doesn't look like it's quite canonical SBGN, but it's close. Again, so we can see how this I'm actually not sure what these arrows are supposed to mean. Like, does that mean that EGFR plus ERB goes to all 3 of them at once, or anything? Anyway, so if you have to probably look at the actual model to know what's going on specifically. That's what happens when you don't have standard graphics. Like, either this is becoming this, or it's influencing this, or something. Met goes to Met too. Anyway, these are some graphs that they have generated from the model. So, here, the original model is, you can click on that, and then this is the sort of the standard way. If you look up a model, this is what you'll get. This is the overview. This is the short description. This is basically the, I think this is actually written for biomodels specifically. Sometimes you'll get just the abstract of the paper here and other things. On the right, the metadata information is sort of how it is annotated. It is described by as particularly important because it will usually link to the actual article that it comes from. So this is described by PubMed this. We can click on this and go to the original paper. And of course, this is just the abstract of the paper. If you want to find the actual paper, you usually need to do just copy that, go to scholar.google.com, paste in the title, and look, there we go. You can see the whole thing is HTML. So there's the abstract, and then we actually have the full paper here. Talks about the thing, and then here we have, there's the graph. You may recognize this from their front page, the model of the month thing. And here are the actual reaction things. Let's look at the high-res image of this so we can see what's going on. So this is sort of a general schematic of the system. And then here are the actual reactions here. EGFR dimerizes, ERB3 dimerizes, EGFR and ERB3 combine to form a dimer, etc. Those sorts of things. Okay. So we were able to find the paper itself, yay. It is also going to be annotated with particular things about the model, so about the system that it's describing. So it's lung, it's adenocarcinoma, it's definitive, which I don't know what that is, but since I don't know what it is, I will click on it and we'll try to find out more. It's niloquinazoline with anti-neoplastic activities.
It's a drug that inhibits EGFR.
Okay, good.
It's a cancer drug. Yeah.
The anti-cancer drug. Anti-neoplastic activity. Perfect. So yes. So that model has this in it. If I were to look up that particular NCIT definitive, I could look up all the biomodels that involve that particular drug. So maybe if it's a general anti-cancer drug, this is the model of how it works in lung adenocarcinomas. Maybe there's another model of it, how it works in other systems. So great. So let's go back. Oh no, actually I do want this. Stop. So the other thing is that you can look at the actual files that it has, and there will be a model, and for every biomodel there's going to be a model file that is the basic thing here. And we can look at it in preview, and here is the SBML. There's all our general description. My phone. Hush phone. There. All right. And then here's the actual bulk of the model. We have a bunch of function definitions. We have more annotations of what are these things? Just bags and bags of annotations. Here's our parameters, here's our reactions, etc. It's not the most useful way to look at a model, and we're going to do it differently also. So let's go back to browse all models and do a search. So here here's a bunch of models. This is just everything, like everything from the curated, manually curated, non-curated, and manually curated branches. You can see that most of them are SBML. They have a few that are others. They have some MATLAB or Octave version things. They have combined archives. Most of them are going to be ODEs if they're tagged of anything at all, etc. So let's say that I am a infectious disease expert and there's a worldwide problem. Then I'm wondering if there's a model about that. So I will type in my problem, which of course is zombies, and search for results. So here we have 4 models of zombie outbreaks. And you'll see that like 3 of them are from the non-curated branch, and 1 of them is from the manually curated branch. I can tell you that because of the ID, anything that's with an ID of biomod 000 is going to be the curated branch, and before it gets curated as an ID of model 100 something. So these are our different zombie models. I checked earlier, these are actually all from the same paper. So let's look at, well, if I check this, then it'll filter and just give me the manually curated model. So here is my manually curated zombie outbreak model of SIZRC. Is the model with a latent infection and cure for zombies described in the article. So go over here, is described by ISBN this. We click on that and it takes me to the ISBN database, and it doesn't actually look it up. So I'm like, okay, well, maybe I'll look it up then. Copy the actual number, paste it in, and look, it's a book on infectious disease modeling and research progress. I could buy it for $89. I don't want to buy it for $89. This is just a demo. So let's find another way to get it. Here is a link. We'll try that. Page not found. So as you can see, like not all these are great, but let's just copy this instead and use our old pal Google Scholar. And great, here's a PDF of the actual thing. When zombies attack, mathematical modeling of an outbreak of zombie infections. Great, I now have something to protect me against the ravening hordes, is a model of what's going on outside. So we're scrolling down just to sort of get a sense of what's going on here. The base class is susceptible, zombie, and removed. So basically normal humans that have been turned into zombies, and removed, which is a euphemism for dead. And here's our model. We have susceptible people that can turn into zombies. We have zombies that can die. So the susceptible people are being born at some rate. They are dying at a certain rate, and they are turning into zombies at a certain rate. Zombies are also dying at a certain rate, and they're also being resurrected at a particular rate. So this doesn't look good for the home team, because if it doesn't matter how you die, you can get resurrected as a zombie. There's not going to be much we can do about that, just based on the model here. So it talks about some equations and stuff, and I think it's going to give me a graph. And this guess doesn't give me a graph here first. So here is a wonderful graph. The case of no zombies. However, this equilibrium is unstable. So we have 0 zombies and 500 susceptible people, and just nothing changes. Now, looking at that model, I'm already a little suspicious, because like if people are here, and if they're dying at a certain rate, and if people that are dead are being resurrected as zombies at a certain rate, it doesn't matter. Like this rate doesn't depend on the concentration of Z. This rate doesn't depend on the concentration of Z. Zombies are going to be produced somehow anyway, even if they start off with 0. So I'm like, wait, so what's going on here? In the infected disease model, we have humans to infected, and then so the humans die at a particular rate, and the infected also die at the same rate. You notice delta is the same here, but based on the other population. The infected then turn into zombies. The zombies then can also die, but they can also get resurrected. And here we have a nice little graph of people when we start off with some zombies, and then the population crashes and the zombie population increases. And some more graphs about that. Then we has a model with quarantine. So here we have a model where it's like, if once you get infected, you get thrown into quarantine. Or if you find a zombie, you throw them into quarantine. And then quarantine people die at a particular rate. And that's all, like once you're in quarantine, you're just going to die. But then again, still, once you're dead, you might be raised as a zombie, and it didn't matter if you were in quarantine. So you might expect that that doesn't do much to your model. And indeed, like the onset of population crash is a little bit later, I think it says. But those zombies just go up. And in fact, here they're going up to a higher level. So, and if you remember what it told us about, where was I here? This is supposed to be a model of latent infection and cure. So here we have a model with treatment, and now we've introduced zombies back to normal people, but they are normal people that haven't been cured, completely cured. They can still get reinfected. And in fact, I think that says, it says we have no treatment, but we no longer need the quarantine, but the cure will, this is interesting. The cure will allow zombies to return to their human form regardless of how they became zombies in the first place. If a person just dies, they get raised as zombies, and then they get cured, we now have resurrection. So that's nice. There's a little silver lining in the zombie outbreak. And then it has the impulsive eradication thing, which I think is one of the other models that was in the original. So we have a basic idea now, sort of by looking at the paper, of what sorts of things we're going to be modeling. So let's look at the files. Here we have a bunch of files. The model itself is here at the top. And then we have an auto-generated PDF file. Let's look at the auto-generated PDF file. That looks interesting. And this was created by a program called SB-Multi-LaTeX, which goes through the model and it sort of pulls things out. It tells you how many compartments there are, how many species and constants, like all the different SBML elements. And it like pulls out the annotation paragraph here that it had at the beginning. It tells you what your units are. Like one of your units is individuals, which you might expect. A unit of days instead of, or something happening per day. Let's see, thousands of intervals. Tells you also about length, tells you about the parameters. So if you, again, wanted to sort of get a general overview of what is in this model, and it has generated, many biomodels have these SP multi-LaTeX files automatically generated for you. If you want to run SP multi-LaTeX yourself on a file that doesn't have it, you can do that. I see a chat thing. We haven't talked about compartments yet. Compartments are, so SPML assumes well-mixed compartments. So in other words, we assume that we don't have sort of diffusion over space. We talked about like everything happens in a cell, the cell is well-mixed, say, or for humans and zombies, we're going to assume that they're like the humans and zombies are freely mixing and we aren't having enclaves of humans and enclaves of zombies. If we did, then we would, if we want to introduce that to our model, we could, but then you would introduce new compartments. We haven't talked about compartments, and I guess that's sort of an advanced topic, but usually you can get away with sort of the default general compartments. All right, I'm gonna close that. Biopacks, versions, the Scilabs, there's a lot of auto-generated versions of these things, including, I think, what did I see? Oh, like a generated .m file or an octave file, which could also be, octave is sort of the publicly available version of an open source version of MATLAB, or they try to be. So this is the version, if you wanted to run this in MATLAB, you could, and there are other, this is an auto-generated thing from a while back, but if you wanted to there are modern conversions of SPML files to octave and MATLAB as well. Chat. Yeah. Thanks for answering that. And we have like the old XML file. So this is the original version before we switch to this. So that might be something to look at some point. We also have the Copasi file. So this is just the Copasi save file. And if you want to run Copasi, biomodels in particular, their curators tend to use Copasi. So they will often, I think in at least half the biomodels will have some Copasi save file in here. And if you just download that and load it into Copasi, then you'll be able to actually like see what they were doing in Copasi at the time. We, as a lab, we are working on improving biomodels itself to have links to actual places to simulate things. So you could actually simulate your model online. So expect that in the next year or so, hopefully less than that. So if I want to pull this into Tellurium, the simplest way to do that is to give Tellurium the URL link. I could download it and then try to upload it to the machine, but I'm going to right-click on this download link and copy the link address. And then I'm going to close all these other tabs except for my PDF. And I'm going to go to the biomodels demo. I'll go ahead and run all here. All right, so I can start that. And then instead of load A, I'm going to load S and put in that URL. So this will load the SPML file into Tellurium. And then I'm going to simulate and plot it and see what happens. Here, see what's going. Any other questions so far? While we're waiting for this to do a thing. There we go. That actually ran the original version of it. So bam, here we go. You notice that the graphs in the paper only had susceptibles and zombies. Here, since removal group, in other words, the dead, since it's another species in the model by default, we're going to show that. I'll go ahead and leave that in there. If we wanted to exactly reproduce the figures, I would just take out that graph. So if we look back at the zombies thing, we can see graphs that look very similar to that. So yay. So from here on out, I'm just going to demo like what it would be like to play around with a model that we've pulled off of biomodels. So let's get antimony. Oh, and that's the unviewable thing. So we're going to print. There. So there's our antimony version of the model. And we see, again, the compartment is the default compartment. Like, again, antimony sort of assumes a default compartment and hides all that information from you. So you usually don't have to worry about it. But you'll often see it in imported models. It's just, it is the volume that you are doing things in. So we have birth, the creation of susceptible people, the zombification. So this actually looks sort of interesting. Zombification is a reaction that creates zombies out of nothing. And that's not how the paper works, right? Like this, here's our model is supposed to be with latent infection and a cure. Zombies aren't created out of nothing, they're created out of infected people. That's the inner rate. So if we go back to the demo, we see, well, and the other thing that we notice is that our species are just susceptible zombie and removal, and that's it. Like, we don't have the infected thing. And in fact, if we start looking at this more, it turns out this is not the SIZR model, it is just the SZR model. So if we go back up here, so despite what the description said, looking at the biomodel, this is actually all we have. We have S and Z and R, and Z is being created, but it's still, zombies aren't being created out of nothing, they're being created out of susceptible. So what's up with the model here? So you see zombification, and then you see susceptible to zombie or death. So basically this is modeling the disappearance of the susceptible population to nothing. It's basically doing it as a straight ODE. Like, this is DSDT, and this is also like DZDT, right? This is the change in zombies over time when they are created. This is, and it's broken into two parts. This is the creation of zombies, and then this is the destruction of zombies. This is the creation of susceptible, and this is the destruction of susceptible, but it's lumping everything together into one thing, into one reaction. So, and indeed, we have function for susceptible zombie or death, beta, susceptible zombie delta. Oh, here. So another thing about this model, and you'll see this like literally every time with anything that's been created in Copazi, is that all of your reaction rates are going to be some function, and then the function is going to be defined up here. And that's great if you want to look at the function, or if you're going to reuse the function. But this, I'm going to have to take a drink. But for here, we have like literally a new function for every different reaction, which, so you're not actually reusing anything ever. So let's see if we can get rid of that. I happen to know how to do that, and so I can do that, and I did something similar earlier. So I happen to know, and I will let you know also, that there is a function in libSPML to change all of these functions to sort of make them in line. So let's look at the libSPML repository. And indeed here. So this is a little, like, is somewhat cheating, but if we go to libSPML, this is from the SPML team. This is the official version of libSPML. If we go to the examples, we can go from the examples to Python and see a bunch of example scripts for doing stuff using libSPML. So this one looks useful: inline function definitions. And that is indeed actually what we want. Here is a Python program that will give us inline function definitions. So we look at this, it's like has arguments to the function. It's checking to make sure the file exists. We create readers and writers. So here we go. We create readers and writers. We read the SBML file into an SBML doc. Check to see if there's errors. We're not going to worry about that. And then this is the meat of the thing here. We're going to, yeah, sure. Just copy this core into our program. So this is basically what we want. We need to fix the indenting. And we're going to need to import libSBML, which should have happened. I mean, it should have been installed anyway. We're going to need the SBML doc. SBML doc. Read. Is that going to give me a? Ah, there we go. Oh, come on. Okay. Here, I'll go look at this thing again. Pretty sure that it's just SBML reader, read SBML. I think there's a shortcut also. You know what? See if that works. Hey, look, doesn't like that part. So I'll just comment that out for a bit and try that. That worked. Yay. Okay. So load S and SBML. Right. String, because I happen to know that function exists. And nope, does not like. Okay, I did this earlier and I have it. No work for us. Nope. Oops, this is T. All right, still doesn't like the right SBML string. Oh, right. It's a function from that. There. Whew. All right, got it. So now we have, and look, we don't have all those function definitions. Yay, we just have, so now we've converted this with all those functions, so we can't read it as easily, to now we just know what the function is in here. It seems to be just using compartments here. So now I'm going to copy that. We'll just copy the model and we'll do a new thing here. And we'll do r equals d.load a, paste in the model, and go from there. r.simulate plot, see what happens. Good. So we've managed to convert it a bunch. It's now in an antimony form. We can see what happens. Let's see. So one of the things I was, if you remember, when we were looking at this, we were a little suspicious of this graph. We were like, if, like, it didn't seem like if you started with 0 zombies that you would end up with 0 zombies, because zombies are resurrected from the dead at a constant rate, irrespective of how many zombies there are. So let's see if we can find out what's going on with that. So let's set zombies to 0 and run that and see what happens. And indeed, look at that. Susceptible, no zombies, no removal. However, we know that there's a birth rate. we know that there's a death rate, and we're not seeing any changes at all. So maybe the problem is just that we haven't simulated long enough. So let's try simulating to 20 instead of just 5. What's happening there? Oh, look, if you go out far enough, suddenly the human population crashes and the zombies here, even though we started at 0. This graph looks basically the same as that other graph. So we can now check this and say, like, the case of no zombies, this equilibrium is unstable. That's no equilibrium. It's not an equilibrium. It's not an unstable equilibrium. It's just slowly changing in time. And like, if you have zombies rising from the dead at a constant rate, you will get zombies because you will have, assuming you have any dead people, and there is indeed a death rate. So that's what happens there. And in fact, like, there was a birth rate and we're not seeing anything change. Like the sum total of everything seems to be pretty close to 500. So we had 500 people, they all turn into zombies and the dead, but there was a birth rate, and the birth rate here in the paper, at least, right? It was just pi. There is a rate at which people are born. We don't seem to be seeing that at all. So let's see if we can see that. Here, we're gonna copy that, r.reset, and then we're gonna go to 200. Let's just do this a few times. We'll go to 200, and then we'll go to 2,000, and then we'll go to 20,000 and see what happens. So now we see what happens like over a longer period of time. This is all they published in the paper, right? Human population crashes, zombies and the dead, zombies appear, and we can also see the dead appear. But if you go a little bit longer, you start to see zombies starting to increase. And if you go long enough, zombies increase even more. And if you keep on going longer, the dead are actually at a constant, and the zombies are like getting more and more. Basically, what's happening is that our birth rate is actually kicking in, and everyone that's born immediately turns into a zombie. And we have like a constant level of dead and an increasing number of zombies over time. Now, maybe this doesn't matter. Like, what they're trying to model, they're modeling in continuous space something that actually happens on an individual level, on a population level. So they are mostly interested in like, the human population has crashed here. We have in our model a birth rate, but a birth rate that doesn't depend on the number of people. But if your population goes to 0, you're not actually going to have a birth rate. So basically, this is sort of illustrating that the model is wrong, but it also sort of indicates like this is the part they cared about. But if we wanted to make a better model, we could say like, you know, what if we fix that? So what is our P? Our P here is 0.05, right? And let me try to find that. Here's our birth rate, right? Our compartment underscore is 1. So I'm also going to simplify this by just removing the compartments to make it easier to read. Because who cares? And if you look at the history of the Wolf model that I had, you can see that I did the same thing there. One of the earlier things was I deleted all the compartments just because clearly it's not part of the model. We don't want to look at it. So we still get the same graphs. Everything seems to be working. So great. So here's our birth rate is like creating people at a rate. Let's make this, and I can't spell susceptible on task, so I'm just going to make that susceptible times P. Now we know that in their model, the P was happening with the population of 500 people. So what I'm going to do in order to make it the same rate at the beginning, I'm going to divide P by 500. So, oops, here we go. So if I divide that by 500, that should give us exactly the same birth rate at the beginning of the simulation. But then as the human population crashes, the birth rate should also crash. Because we're modeling things out further. They didn't bother putting this in, but we are, for whatever reason, interested in what happens later. So hey, look at that. And actually, interesting different dynamics appear here. So here's our original thing. The original thing is indeed everything stays the same. But now zombies start to die. No, zombies start to increase. We start to get to where there's an equilibrium between, because the dead keep rising as zombies, even though the zombies have their own death rate. We now see that in their model, there's a balance between zombies and the dead that highly favors the zombies, at least over longer periods of time. And we aren't even at equilibrium here yet. So let's add yet another thing here, go 10 times longer. And indeed, so here we finally at equilibrium again, and all our humans have been turned into living zombies. There's very few dead here. So clearly, what this model is pushing towards is there being no dead people, they're just being zombies. Let's see, it's 10:30, stop at 11. That's probably, so that's sort of an overview of playing with a model, looking at things, like figuring out some mistakes, but and there's there's a lot of problems with the model, there's a lot of problems with the paper, but one of the interesting things that I want you to take home message here is, because there was a model, I could in 10 minutes figure out what some of these problems. And I could look at the actual paper and say like, oh, you're not accounting for this. If you did, this other thing would happen. Like I can look at the paper and fix things. So if we go back here, we could actually, it seems like we could probably pretty easily make what this was supposed to be, the SIZR with a cure. We could either try to reproduce what they've done here, which wasn't quite done in biomodels, or we could, you could try to reproduce things, or you could try to reproduce things and then improve. Like what do you play with things? What happens if the rate at which, or say like once a zombie dies, you could make a new model in which if a zombie dies, that corpse can't be resurrected as a zombie. So we actually split our dead into two populations. So we could say like, if a susceptible dies, that is not, they won't rise as zombies. Only, well, we could say that like only if an infected will either go straight to a zombie or will die and then be resurrected as a zombie. We could make that model. And then the zombies could die to a different population of dead that won't resurrect the zombies. The susceptible dead and the truly dead, basically. And then you could, I don't know, publish your own model or figure out like what they're doing. And obviously this is a relatively simple and silly example, but you can do this with the COVID models also, or with any other model. You can look at the paper, say like, what are your assumptions? What are they good assumptions? What happens if I tweak this thing? And it's not that hard, at least not for models like this. And even for like the Wolff glycolysis model, that's another thing. If you wanted to just look at my commit history or the model, here, the answer to the source control exercise, you can see how I changed it over time. And actually I did a bunch of stuff with the biomodels thing last night, and I'm going to put that in here as well. All right. I think what I'm going to do from here is I'm going to make a breakout room. I'm going to go to the breakout room and just sort of live demo messing with the zombie model some more. So if you were interested in seeing me mess with the zombie model, you can do that, and you can ask questions or whatever. But as the exercise is, so the exercise for you to do instead, if you don't want to watch me mess with zombies, is search biomodels for a model related to your own interests. You could either look at one of the other zombie models, COVID-19 model, or anything else, that maybe anything you're interested in, anything that piques your curiosity. I want you to find a paper, convert that model to Antimony so you can look at it, maybe simplify it and start playing with it. Try simulating things and see what you can do. Let's see here. And in the meantime, I think I can make a breakout room. I will let participants choose the room. I'm going to create one breakout room.